But there's two kind of key ideas that we want to get through today. We already introduced one of them yesterday, which is this idea of an expected payoff. Okay, I decided after kind of reviewing what I'd done in the last couple of years and looking at the schedule for the next while, that it might be worthwhile keeping on with this idea of an expected payoff, and then do the stuff about probability inference and learning in games when we come back. Okay, so this material is in Chapter 7. I'm going to put it at the end of yesterday's lecture, okay, so please don't copy it down. It'll be up there on the web. It's just to remind you kind of what we did with that little card game. We're sitting there trying to think, well, games that have uncertainty in them, people don't know exactly what's going to happen, okay? And how do we think of their payoffs? Remember, we got the PDIP structure. What are the payoffs? What can they do? What's the information? Who are the players? What can they do? What's the information? What are the payoffs? We got this idea that in the card game, if the red player folded all the time, or folded and raised and folded, or raised and raised, depending on whether she saw a club or a spade, there'd be a bunch of strategies for her. The blue player has also some strategies. In this game, it's simple, meet or pass when you get a chance to move. But if we kind of mapped all of the outcomes in there, we'd see that the outcomes for each of the players are really uncertain for them, okay? So we call that a contingent payoff. And that is actually a really fundamental idea in thinking about games of strategic interaction, is when there's uncertainty, is they don't know the result, okay? They don't know what's going to happen. So, for example, think of your grade point average, okay? Think of it in this, or your grade on this exam, okay? And let's just think letter grades. So you get an A, you could get a B, you get a C, you get a D, you get an E, and it's probably even lower letters you could get, but let's just say those are the 5 letters. So those are kind of outcomes, and we could put numbers on them, but those are the outcomes of the game. And then the game is, you study, maybe, you put in some effort, maybe, you've learned some things in the course, maybe, and you put all those together onto the exam with a bunch of questions that I've set, and I've set these questions trying to go through, people who put in some effort and they seem to understand, and whatever they should do, well or not so well, depending on the day. But basically, it's kind of your effort and intelligence that matched with my marking. Either I'm going to mark tough or I'm going to mark easy, okay? And those things will, at the time that you're sitting writing the exam, at the time I'm setting the exam, I don't know what they're going to be. You don't know what they're going to be. So they're contingent, okay? And so that's a good way. It's just, it depends. That's the idea of a contingency. And so there's uncertainty about what the outcome of this interaction is going to be, and it's at the level of contingent payoffs. But then we go one step further in this theory. We try to say, look, contingent payoffs are a real pain in the butt to deal with, because how do people evaluate them? How do you deal with when you're making your choices about your effort and amount of study and what exactly you're going to say in the exam with these contingencies, It's like you're sort of thinking, if he marks hard, I'm going to die. If he marks easy, I'm going to die. No, that's the dominant strategy of dying. You don't know exactly what's going to happen, okay? And how do you deal with that? Well, you might think, I got to pass this course. It's my last year at varsity, and if I don't pass this, I'm dead in terms of getting a job or getting out of here. Or you could sort of think, I just took this elective. If I lose it, it's really no big deal. And those kind of attitudes will affect the risks you're willing to take for studying and actually performing on an exam. And what we're trying to capture here is that these are just possibilities for outcomes, okay, the contingencies. What we want to do is capture a person's attitude towards their uncertainty here. And what we did is we introduced this idea of an expected payoff. Now, behind the idea of an expected payoff are people's beliefs. Remember, we already touched on those because we've gone to the Nash equilibria and the strategy idea being both beliefs and actions. So fundamentally, what we're going to do is use the language of probability to talk about people's beliefs. One of the ideas that comes out of it is an expectation. Okay, it's a probability-weighted average of something. And so you say, well, what about the probability-weighted average of my grades? I get a 10% chance on an A and a 20% chance on a B and a 60% chance on a C, then you could look at your expected grade. Now, I deliberately chose letters rather than numbers because you say, what's a probability-weighted average of letters? Good question. Okay, what does it mean? And always when we're thinking of payoffs, you should ask, what does this number mean? Because 50-50 average of -1 and 1 is 0, and that's what that number there is. Okay, and similarly, a 50-50 average of 1 and -1 for the red is 0, and that's what that number is. So you can calculate the number, but you want to ask, what does it mean in terms of the person's payoff? Well, to keep things sort of simple, we've got this complexity about visual uncertainty, and then we've got what are their beliefs, so how are they going to evaluate these various uncertainties. And what we do is we say, let's just take a probability-weighted average of the things they're going to get in this game, of the outcomes. And that's called an expected payoff. And it turns out that there's an assumption there about what we call risk neutrality. I'm not going to go into the definition of that in today's class, but we will come back to it. Because one of the things about games is when you're interacting with people is, how much risk are they willing to take? Are they kind of indifferent to risk? Or are they kind of afraid of risk? Or do they like risk? Okay, those ideas of risk-loving, risk-averting, or what we call risk-neutral will be key elements of any kind of game. Often we'll make the assumption that we're just going to assume people are risk-neutral, which means they take probability-weighted averages of whatever it is the outcome denominated in, which could be money, could be chocolate bars, could be preference ranks. Okay, but there's an assumption there about what the other player's attitude towards you in the game is, about their payoffs. Okay? So anyhow, we get this, we're translating from these contingent payoffs into the expected payoffs. And then we take a breather because we think, oh, I can do this. It's a simultaneous game, right? I put in the best responses here for going across the rows. Zeros are better than zeros, or worse than zeros. Best responses are all zeros. Here, 0.5 is better than -1. I mean, we could do this analysis, and if you do this analysis, you'll see there's no Nash equilibria in the pure strategies. And what we're going to do today is talk about an important concept called mixed strategy equilibrium, but it does build on this idea of probabilities, okay, and people's beliefs. And in particular, we've met this before back in this game we had with no Nash equilibria. And this, in the text, this is called a tennis game, which is why you're watching that video. But we're going to spend a little more time looking at this tennis thing in a second. And then in class, I just talked about this idea of a rugby game match where in a line-out, people could throw long, throw short, defend long, defend short. And this idea was that the red player here was throwing short or long, and the blue player was defending short or long, and these numbers were success percentages. Now, it's the same in the tennis example in the text, where the red player can go down the line or cross court, and the blue player can defend down the line or cross court. Now, it's easy to kind of trivialize that, but in a simultaneous game, there is no Nash equilibria here, right? If the blue guy goes short, the red guy should go long. The red guy goes long, the blue guy should go long. If the blue guy goes long, the red guy should go short because 80 is better than 20, okay? And if the red guy goes short, then the blue guy should go short. And then it's like that circular reasoning. It's like, well, if he does this, then I should do that. But if I do that, he will do this. And it's just, you keep going around in a circle. Well, the mixed strategy idea will help us think, well, okay, there are games like this where it's actually quite tricky to come up with a prediction, but there is a way of thinking about it, okay? And it introduces this element of surprise. So, especially in sporting matches, here, rugby players are going to throw short or throw long. You want to keep it masked right until the last minute, okay? Similarly with the defensive team, they've got to make a decision to defend short or long. They want to keep it masked right until the last minute. And it's that way with tennis too. So what I did is I have several vices in life, but one is I like watching tennis, okay? So I forked out some money and I pay for some internet pro tennis. And this morning I got up and captured a couple of clips, one of which you just saw with Nadal playing this Portuguese guy Gil. I mean, I didn't watch the game, I just watched the highlights. But what I did do is I captured this, a few bits of footage of this guy, Andrew Murray, playing against another tennis player, Masao. What we're going to do is just watch a little bit, and I'm going to freeze frame it, okay? And we're going to try and think, what's your strategy here, okay? It's hard to see the ball. We'll slow it down in a second. Okay, let's just back it up a bit, okay? So they got this long rally going, and Masao is in the front here. Murray is in the back, and Masao's going to well, when he hits the ball, okay, so he's sitting there, he's trying to disguise what he's going to do. I mean, he can conceivably go to this corner, he can go to that corner, he can go short, he can go long. There's lots of different options that he can take, okay? But in this one here, we just watch what he does. And notice where Murray is positioned. It's like, you know, he's trying not to commit himself to either one side or the other so he can respond. And Masao gets quite a nice cross-court shot there where Murray has to run like crazy to get it. Comes back and manages just to get his racket on the ball, but it's going to be a short ball coming up. You can't see the ball, which is probably good. There, it's just right there, okay, appearing now. So you're sitting here. Here's Masao. Murray's sitting over here in the corner, right? Where would you shoot? Okay, you can go here. You can go here. Let's see what happens. So, I would have been thinking, okay, once you slow it down like this, look at all this open court here. As long as you get a reasonable chance of getting in, which I don't because I'm not a great tennis player, I would be shooting down over here. And watch what happens. So he's disguising his shot right to the last minute. And again, notice Murray, it looks like he's standing there flat-footed. He's not making any effort to defend that in. Now, can Murray read what this guy's going to do? I don't know. Let's have a look and see. Instead, he shoots. Murray starts to move that way. Let's back that up again. Okay, so he's getting ready to hit. Murray looks like he's moving that way, but he shoots the ball right down there in the line. Now let's just watch and see what happens here. So it was a great shot, but it was just out, okay? So let's go back. Remember, what he was doing was at this point back here where he had, he's trying to, he's got an option right here. I mean, we can freeze frame it. You wouldn't want to do this at the speed these guys play tennis, but he has an option, okay? He can go down in one corner or to the other corner. And why did he take the shot here? Well, let's keep going. Just watch another point here. So this is Masao serving. Okay, so here, if you back up to where Masao is going to hit the shot, look at. Let's keep going here. Okay, so Murray is sitting here returning the ball, running like crazy to get back into the center of the court. And Masao, notice the angle of the shot here. Murray hasn't even moved yet, okay? So if this makes it, it's probably, and gets it deep enough, then he's probably going to win that point. But as it turned out, they hit the net, landed on his side of the net, didn't do it. And that's, when we're talking about these success percentages in our game, that's the sort of thing, that's the idea here, okay? You got the right strategy, and the guy said it was a good play, but it didn't work that well. Then there's one more part of that clip where, again, right in the middle of the play, you can freeze frame it, you can see the guy's really got an option at that point. I mean, you can't freeze frame it in real life, okay? But you're trying to mask things, create an element of surprise. That's the nature of the game. Now, in this, actually, let me show you this last bit here, because this sort of intrigued me as I was looking at this, is that this last shot is very much like one of the earlier shots. Okay, so they're playing away, rallying back and forth. Okay, so at this point, again, again, he's got the same idea. What do I do? Do I go across or do I go back towards him? Well, this time he goes across, okay, and executes the shot so Murray can't get it. But he didn't do that the previous time, and that's the idea. Is that, I mean, whatever he's doing, he can't always be going to that open area, because Murray will then expect that, move to the open area, and defend well. Okay, so in that first clip we looked at, why did he shoot it right back towards him instead of in that whole open area on the other side? You know, it's part of the strategy. You have to mix your strategies. You can't be predictable on every one of these points, and that's the idea we're going to look at now. It's like, how much do you mix your strategies? What sort of degree of mixture of your strategy should you have? And we'll see that depends on the payoffs in this payoff matrix. Okay, so let's see how we're going to analyze this game using our idea of expected payoffs, best responses, and see how we can deal with some uncertainty here. Well, if you look at the top, what I've done is I've reproduced the payoff matrix. And here I'm back not to the tennis example, but to the rugby one, line out short or long. And let's say it's New Zealand versus Australia. Okay, so New Zealand throw in, Australia defends. These are the winning percentages given various things that these people do. And their payoffs are their winning percentages. And I've introduced these two other ideas called a P-mix and a Q-mix. Okay, now the symbols P and Q don't have to be disassociated with these two players, but the idea of the P-mix is a probability or a chance, okay, that New Zealand is going to throw short. And then the opposite probability, 1 minus P, for them throwing long. So it could be 10% chance that they'll throw short, and that would mean a 90% chance that they'll throw long. Or 50% chance they'll throw short, just like we did the card game. You know, 50% chance of clubs, 50% chance of spades. So there's these two probabilities. When we think about these probabilities, are going to have to add up to 1. And at the moment, we don't know what these probabilities are. Okay, we're just sort of thinking, oh, you know, there's a P. New Zealand isn't definitely going to go short, and they're not definitely going to go long. They're going to try and come up with some probability of doing that. And the way to think of that probability is like a belief in an action. It's a choice of New Zealand. Okay, somehow I've got to randomize, make it uncertain. But at the end of the day, I'm going to have to go short or long at one point. But right until that end, I want to make it uncertain for the other guy. So I'm going to choose some sort of chance of going probability and some sort of chance of short. And in particular, I want that chance to be what the other guy believes. Okay, so the other guy's thinking, what chance is, and Australia's thinking, what chance is it that New Zealand's going to go short or long? That's what the P-mix is. Okay, what is Australia going to believe? So this P is simultaneously New Zealand's choice and Australia's belief. Okay, and similarly up here with this idea of the Q-mix, the Q is the probability or a probability of Australia defending short or Australia defending long. So again, you know, if we put Q equal to 100%, then that'd be 100% chance they're going to defend short. But if Q is like 50, then it's a 50-50 chance they'll defend either short or long. And if we made Q very small, then the chances of Australia defending small would be small, and the defending short would be small, but defending long would be high. Okay, so we have Q and the 1 minus Q, and simultaneously the Q is New Zealand's belief about what Australia is going to do, and Australia's action, which is trying to make it uncertain for New Zealand to do anything. So the Q's and the P's are the element of surprise in this game. Okay, they're both actions and beliefs. What we've done is we've changed the game. In this first game, we had a 2x2 sequential game where players could either choose short or long in attacking or defense. Now we've changed the game. We've introduced these mixture strategies. Okay, so we look at the chances of choosing long and the chances chances of throwing short, chances of throwing long, chances of defending short, chances of defending long. So what we've kind of opened up the strategy space. It's called a continuous strategy space. Okay, we won't deal with that in any great detail in the class, but yeah, okay, it's just strategies. You know, New Zealand's got to come up with some sort of chance that they're going to throw short or long, and that's also going to be a belief that Australia is going to have some sort of belief about them throwing short or throwing long. Have a look at this graph. I put on 2 lines on here, the 80-20 line. Okay, and why I want you to think of this is that imagine Australia thinking about what New Zealand's going to do, not sure, so the P represents their uncertainty about whether New Zealand's going to go short or go long. And imagine that Australia is thinking, should I defend long or not? Okay. Well, what's going to happen? If New Zealand goes short, I get a 20% chance of winning. But if New Zealand goes long, I get an 80% chance of winning. So Australia's contingent payoffs are 20 and 80. Okay? Now, there are also chances of winning the point or not, but they're numbers, okay, 20 and 80. So that's Australia's contingent payoff if they decide to defend long. Notice that their contingency, 20 and 80, depends upon what the other guy does, okay, short or long. They don't know what they're going to do. They can't see it. It's a simultaneous kind of game or it's masked. So what they can do, though, is think about it and have some beliefs. We think, well, what beliefs are reasonable to hold about what New Zealand's going to do? And work something like this. Supposing you believed that P was 0, okay? The chances of New Zealand throwing short are 0. That means there's a 100% chance they're going to throw long. So if you defend long, your payoff is 80. Okay? So what we do on this graph here is we look on the axis down here and look at the probabilities, the P-mix for New Zealand, that is the chances of New Zealand going short, and the chances of New Zealand going short are 0 right over here, which means they must be going long, in which case Australia's payoff is going to be 80. So we put a bullet point there. Just forget about the line for a second, because let me do the second, another point, and we'll come back to why we're putting in this line here, okay? Supposing it's a 10% chance now that New Zealand goes short. So we're thinking 10% chance that New Zealand goes short. Well, for Australia, it's going to be like a 10% chance at 20 and a 90% chance at 80. Okay? And so we think of what's their expected payoff. Well, if they believed it was a 10% chance that New Zealand was going to go short, so we put a P of 0.10, then them going long is 90%, so their expected payoff is 0.1 times 20 plus 0.9 times 80. And that's a number, okay? And you get your calculator and you work out what that number is. We can put a little dot here like this. Say, oh, okay, your expected payoff. Now, with a 100% chance on 80, the probability weighted average is 80. With a 90% chance on 80 and a 10% chance on 20, it's a little bit closer to 80 than it is to 20. Okay? And if we keep marching up here, what about 50-50? Well, 50-50 is going to be halfway between 20 and 80. So if you believed it was 50-50 and New Zealand was going to go short or long, your expected payoff would be halfway between 20 and 80, which would be exactly 50. That's that green point there. What if you believed an 80% chance of New Zealand going short? Then what we'd have is a gamble that has chances of going short are 80%, which in case you make 20. The chances of going long are 20%, in which case you make 80. So we've got a probability weighted average of 20 and 80, but now it's heavy on 20. Okay? And so we have this line, okay, that goes from the left to the right. The blue line is, you can think of the whole line as the expected payoffs. Now this is the way, in uncertainty, we are going to think about players' payoffs. We're going to draw lines. Okay? We're going to say, oh, we don't know what they believe, but they could believe 10%, 20%, 30%. And then for each one of those, we'll calculate their expected payoffs. Okay? And it turns out here, the expected payoffs all lie along a line between 80 and 20. And we call, okay, I'm just going to put a label on that. And let's read the label. The label is E for expectation and U for utility. The utility here is just payoff numbers, so we have an expected payoff. Okay? So we're looking at the probability weighted average of these numbers. That's their expected payoff. It's Australia's utility, and the utility they get depends upon what New Zealand does, okay? Or the value they get out of these risky situations depends upon the chances P. Again, we don't know what those are. If it's a 0% chance New Zealand's going short, then and Australia goes long, then they're getting 80 for sure. But as the chances of New Zealand going short get higher and higher and higher, the weighted average is going to get closer and closer to 20, and so going long is going to have a bad expected payoff over here and a good expected payoff over here. So, but it's that line that you want to be able to get hold of, okay? And usually when we're looking at these simple examples, it'll be, oh, I need to draw a line between 80 and 20, and along that line is the line of expected payoffs for Australia choosing long. Okay? What if they chose short? Well, if they choose short, to defend short, then they're either going to get 50 or 10, right? But of course, they get the 50 if New Zealand goes short, and they get the 10 if New Zealand goes long. So again, their actual payoff is uncertain. It's a contingency. It's either going to be 50 or it's going to be 10. But you could think of a probability weighted average of those numbers that lies between 50 and 10. So let's put the 50 and 10 lines in. So again, we've got some black lines let me just get rid of some of these other numbers here. So far what we've had is this blue line is the expected payoff, the probability weighted average payoffs for Australia, the way they calculate their contingencies if they go long. Okay. On the other hand, this is the expected, we're going to draw a line for their expected payoff if they go short. Now, what happens here is that supposing we take the P equals 0 line. Okay, if P is 0, the P mix is 0, then 1 minus P must be 100. That means there's a 100% chance that New Zealand is throwing long, but they're defending short. Okay, that's a bad payoff for them of 10. So the 10 is right beside the 0. On the other hand, supposing we have a 100% chance on P, so we're going way over here to the right, then 100% chance on P, if Australia throws or defends short, then their payoff is going to be 50. So we put a dot up here at 50, and we draw a line here between the 10 and the 50 going this way. Now, you can see there's 4 dots. Okay, there's a dot here, there's a dot there, there's a dot there, there's a dot there. There's all kinds of different lines that you can draw, and for exam purposes and for little calculation things, I'm hoping you can join the dots correctly, okay? So that when we're looking at these games of uncertainty, you'll be able to say, oh, if Australia goes short, the contingencies are 50 and 10, and if there's a high chance in the 50, that's a good expected payoff. That's over here to the right. But if it's a low probability of going short, then it'll be a high probability of going long. That'll be a bad expected payoff, so low probability of short, bad expected payoff. So as the probability of New Zealand's going short goes from left to right, if they're defending short, their payoffs are going up, but if they're defending long, their payoffs are going down. Okay? And so what you can think of is, oh, well, if the chances are high that New Zealand's going to defend short, then clearly it's better to defend short. And if the chances are low that they're going to throw short, then it's better to defend long. And you'll be right. We can put in what we call a best response line. Okay? Just take a second to grasp that idea, because it's just what we were doing before. Okay? Remember we had our little payoff meter, so we say, well, if this guy did that, then we calculate our best response, and if he did this, we calculate our best response. Well, here, we're doing the same thing. Only now we're trying to think, okay, if the probabilities are over here, that they're pretty small, particularly this number here turns out to be 0.7, okay, where these two lines cross. If the chances are less than 70% that New Zealand is going to play short, then it's better for Australia to defend long. Now, when they defend long, okay, it could be that New Zealand actually goes short, okay? Because this was just a probability choice, you know. It could be that they go long. But given what they believed, they were making the best response. You know, they thought the chances were pretty low that New Zealand's going to go short, and they decided to go long, okay? Whereas over here, they thought the chances were high that New Zealand should go short, and so their best response is to defend short. And once we have these best response lines, we're back in territory that we know. It's like, oh, people can make best responses to their beliefs. Now, what happens right here? At this point, if the probabilities of New Zealand throwing short are about 70%, right at that crossover point, then basically Australia won't have a best response, will it? It's like, should I defend long? Should I defend short? Well, it's clear to defend long over here, and it's clear to defend long over there, so defending short is unclear. Okay, you're indifferent, which also means you don't know what to do. And that's the level of uncertainty that New Zealand needs to aim for in this game, is to make it so Australia has no clear choice. They don't know whether you're going short, they don't know whether you're going long. Or in those tennis examples, the idea is these guys have got to mix their strategies, and they will do it on the basis of what they understand the success percentages of these other players. So I'm sure they have their trainers going over videos like this, someone like Nadal is successful all the time, but it's like, some people have weak backhands, some people have stronger forehands, they do this shot well, that shot well, and it's like they're working out, okay, given those things, what are my chances of winning a particular point against this guy? What's my strategy? Okay, how much do I need to mix it around? Okay, so that's how we get if you like, a best response function for Australia against a PMIX strategy for New Zealand. Now, there's a little graph in the handout that has the Q mix on the left-hand side and the P mix on the bottom, okay? And the Qs are going from 0 to 1, and the Ps are going from 0 to 1. I put a little grid in on top of that. And what I want to do here is just track the best response of Australia in this graph to any choice of the P mix or any belief about New Zealand's probability of going short. Okay, so we're going to put New Zealand's strategies on this axis here. Okay, that P-axis is the P mix, which is, okay, how likely is it that New Zealand's going to throw short? Well, it goes anywhere from 0 to 1. And if P is on the left-hand side, then Australia should be using the long strategy, okay? So the Australians, then, if you think of what their strategy is as a Q mix, they should never really be going short. They should always be going long. Okay, that's a 100% chance on long, which is a 0% chance on short. Okay, let me say that again. We're going to represent Australia's strategies as a Q mix. Remember, Q mix is their chances of going short. So if they're always going long, then the chances of going short are 0. Okay, so that's what we put in along this axis right up until the P of 0.7. And then for P's above 0.7, Australia wants to go short, which is a 100% chance. Okay, so their best response is jumps way up there, and I've sort of highlighted it up there. So for P's in this region, this is Australia's best response. For P's in this region over here, this is Australia's best response. And right at P equals 0.7, they're indifferent. Okay, it doesn't really matter whether they go short or whether they go long. And of course it matters, I mean, in the actual play of the game, but in terms of their thinking about what's my payoff in this game, okay? Well, obviously, I have to make a choice. New Zealand has to make a choice, but my expected payoff won't matter if New Zealand is creating chances of 0.7, or if I believe that it's a 70% chance that New Zealand will go short. Then it won't matter, so I just put a continuous line through up here, right? Okay. So that is a best response curve, which is just going to be like those X's and O's that we had. Remember, if I got rid of the best response curves just for a minute, and I was just looking at this as a grid, and I was saying, okay, put it over here are the role players' strategies. Over here are the column players' strategies. You know, tell me what the best response is of the red player to every strategy of the blue player. You know, you'd go through and tick some cells here like this, and that's what these curves are. They're just best response curves like the X's and O's, but they happen to be continuous curves here. Okay. We've analyzed half the problem, because what we've done is we've taken this game where now the strategies are much larger than what we call pure strategies. There's mixed strategies. We've analyzed it from the standpoint of Australia. Now let's look at it from New Zealand's standpoint, and that's what the other graph does. Okay. In this graph, on this axis, is a Q mix, which is what chances are of Australia defending short or Australia defending long. Okay. The Q is on the short, though. Okay. So then New Zealand has to decide, what am I going to do? Well, if I attack short, then I get a payoff of 50, which is a 50% chance here of winning the point. But if they defend long, then I get an 80% chance of winning the point. Okay, so my payoffs are contingent, 80 and 50. I should be looking for a probability weighted average of A and 50. What probabilities do I use? Well, I don't know. I don't know what Australia is going to do. But if they had a 100% chance of going short, then I'm going to get 50. And if they have a 0% chance of going short, I'm going to get 80. So I take the numbers 50 and 80, and I draw a straight line, okay, between them. Let me just get my labels in here. So this line is New Zealand's expected payoff or expected utility. We're going to use this label a little bit before we actually come back and try and explain it in the next term. But just think of it as it's an expected payoff. The expected payoff for New Zealand against a Q mix, it'd be nice if that was blue instead of red, okay, a Q mix of Australia And that's if New Zealand plays short. So that's, remember, it's not an equation. It's just kind of like a little acronym. This is their expected payoff of New Zealand, the red player. So, and we keep New Zealand a little label. We know which player we're dealing with. Against what? What is the other guy going to do? Well, the other guy's going to be mixing with probability Q. And what's the red player going to do? The red player is going to be throwing short. Okay, so it's going to be a probability weighted average of 50 and 80, but it depends where that probability is. If it's close to 0, then I'm going to get 80. Okay, because that'll be definitely Australia going long. And as the Q goes to 100, then 100%, then Australia is going to be defending short, and then my payoff isn't so good. It's 50. It's 50. And, okay. Now let's do the same thing for New Zealand throwing long. Okay, if you throw long, what's going to happen? I don't know. Everything's uncertain in this game, but I got a pretty good chance here, 90% of winning if they defend short, and they only get a 20% chance of winning if they defend long. So my payoffs are between 90 and 20. Okay. Probability weighted average, the 90 is up over here on the right because that's associated with high probability of Australia going short. Okay, which is Q mix of short, so that gives me the 90. But if Q is very low, so I'm over here on the left, so Q is 0. That must be they're defending long, in which case I'm going to get 20. So this straight line is the expected payoff for New Zealand. Okay, is a probability weighted average of their payoffs if they, against whatever it is they believe Australia is going to do, if they defend long. So I'll put that as a label in here, like this. Okay, so now we have two curves. Okay, it's actually finding the points on the curves isn't that difficult if you know the endpoints, because it's always going to be a straight line, okay? And so we think, okay, this is the way we think about payoffs under uncertainty. It's like, yeah, in this game, it really depends what the other guy's going to do. But my expected payoffs are going to be found by probability weighted averages, okay? And then once I get those expected payoffs, I can find the best responses. Well, you know, it depends. I mean, if obviously to the left here, if Q is small, so Australia is going to defend long, then it's going to be better for us to go short, okay? We want to do the opposite that they want to do. And so these are our best response functions. We make our little grid up here that we had before, only now what we're doing is we're saying, okay, what's New Zealand's choice against a Q mix of Australia? So if Q is 1, 0.1, 0.2, 0.3, 0.4, 0.5, and this number turns out to be 0.6 here. So for chances of for Q mixes of less than 0.6, that is less than 60% chance that Australia defends short. If Q is small, New Zealand should be going short. If New Zealand's going short, that's a high P, okay? A high chance, 100% chance of them going short. So for small Qs, we want New Zealand's best response to be over here to the right. If Australia is defending short, less than 60%, so choosing the Q mix is small, New Zealand wants to put a 100% chance on this, on throwing short. If it's the opposite, where up here, high Qs are associated with New Zealand going long. New Zealand going long is associated with a P mix of 0 going short. Over here to the left, when Q is small, New Zealand should be going short. To go short means to have a 100% chance of going short, okay, and that's a high P. Over here, New Zealand should be going long, but going long for New Zealand is 0% chance of going short, which is why we put the red line along here. So all of these are just best responses, little X's and O's, for New Zealand, and their best response when Australia is got a high Q is for them to go put P equals 0, that is to defend long. So we're just translating these things here, which is easier to see, to best responses over there. We put them together with Australia's best response, and pardon this swastika symbol, and we have two best response curves, and what we call the mixed strategy Nash equilibrium is right there in the middle. The idea here is that both of these, this mixed strategy equilibrium is ways of randomizing or creating surprise, elements of surprise, just the right amount, okay? For Australia, the Q mix is 60%, because if they try to defend short any more than 60% or any less than 60%, it's going to give New Zealand a clear choice. Okay, so you want to create a situation where New Zealand doesn't have a clear choice. That is, they're uncertain about what to do. Okay, they're indifferent, but they're also uncertain. They don't know what you're going to do. You know that. They know that. But they haven't got a clear choice. And that's how we figure out what these mixed strategy Nash equilibria are, is that you sort of think, what's the element of surprise where the guy won't have a clear choice? Okay, let me just step back from the sports example. Think of filling out your tax return, okay? I was in a small business actually quite a few years ago. The Apple User Group in the 80s, we did some interesting stuff, formed a company called Magnum Mac, and it's hard being a business person. I'm not a very good business person, okay? I found that out after 2 years, and I eventually got out of the business. After I sold out, they went on to do very well, which is great. But I do remember getting audited by the Inland Revenue. And it was, they don't audit everybody, okay? They have to decide, okay, who's going to cheat on their tax returns or not, okay? And I'm sitting there thinking, should I just put this little expenditure up here, the little expenditure down there? Should I cheat on my tax return or not? And the amounts by which they, I don't want to cheat all the time because then they're going to audit me all the time. But if they audit me all the time, nobody's going to cheat all the time, okay? But if nobody cheats all the time, they don't really want to audit all the time, in which case somebody will want to cheat, okay? It's that circular kind of reasoning. And they have to come up with some probabilities which are both chances that they're going to audit, and which are also beliefs that the other people have about whether how much they're going to audit, and vice versa with the people who are cheating. Okay, they can't have the RD perceiving them to be cheating too much, otherwise they're going to be audited all the time. Okay, so they can't cheat all the time, and that's the idea of a mixed strategy Nash equilibrium. So let's just summarize that. We have a P mix and a Q mix. Now, these are just labels that Dixon and Skeeth use, but the basic idea of the P is it's a probability, it's a chance thing, okay? There's uncertainty in here, and the red P and the blue Q are both elements of surprise that someone's trying to create, but they're also beliefs of the other player. And they're just, once you get that idea, then there's a Nash equilibrium in that, the blue player has to randomize, believing what the red player is going to do. The red player's got to randomize, believing what the blue player is going to do. And in those randomization process, in the mixed strategies, the key thing is that element of surprise. It's like you've got to try and create a situation of uncertainty for the other guy, which is beliefs about what you're going to do, okay, so that they don't have a clear choice. They're just indifferent. And that's the basic methodology of surprise with these mixed strategies. Okay, now next, when we come back, we're going to spend a couple lectures just talking about uncertainty and probability, okay? Because the probability idea is, well, there's uncertainties in games, there's elements of surprise now, but the other thing it adds is information. Well, how do you figure out what your beliefs are in these games? You saw in the tennis matches, these guys are just watching one another. If your body language gives it away, the guy will be able to defend really, really well. And so that body language becomes information. But the other guy's reading your body language, so you'll give him a mixed signal, okay? Like you're going to go cross-court, but really you're going to push it over there.